All right, so I'm just throwing this out here. So we have 100 billion neurons in our brain, and there are 100 billion stars in the Milky Way galaxy. And we know there's a mirror here. Most of us know that the universe is a mirror of the human mind. Now, in a human cell, there's 100 trillion atoms that make it up. And there are 2 trillion galaxies in the known universe, okay? So if we want to fix the mirror, this is a colossal underestimate. So we're going to have to bring that up to 100 trillion. Now, these are light horizons. We see about 13.5 billion in 2 trillion galaxies. Now, they round it up to 13.7, but when you round it up 13.7, it throws all the math off, and this circles out a square. It only works with 13.5, 13.55, or 13.6. And 13.6 is a little out of square, but it all fits right. 13.7 will throw it out 109, and it starts getting messed up around the 5th light horizon. So 2 trillion galaxies and 13.5 billion be 2 trillion here, 2 trillion here, 2 trillion here. Ultimately, you get 16 trillion galaxies. And that's still an underestimate of 100 trillion. So at least you need to multiply it times 6 or 6.25. Now, whenever you go down the list here, this whole light horizon here, these 8, well, ours and then the other 7 is just this one, 108, the top one. Now, what I'm seeing is hardware here. I see 108 gigahertz, 16 trillion megabytes of RAM, which is basically 16 petabytes. But I know that that's a frequency too, so it has something to do with memory and frequency. If you go down the list, you have 108, 216, 324, 432 hertz. That's what that reminds me of. 540 and 648. And 540 is obviously the 554 here, which is 6 times 9 and 27 times 2. So you have 13.5 billion times 2, that's 27, plus 13.5, 40.5, 13.5, 54, and then 67.5, 81, 94.5, 108. So in this aspect, it's perfectly square. 13.55 will work, and then you end up with 0.1, 0.2, 0.3, 0.4. And up here, basically, it'd be 108 billion years. So basically, in this aspect, if you want to use the mirror of humans and the universe would be at least 648 million or billion to 675 billion years old. I mean, we can only literally see like 1/48th of it or something. Literally, the light horizon prevents it. And if we could switch position in time, which is the universe, we can change our position in it, but ultimately the time is still going to go by. And our light horizon is still only going to be 13.5 billion years to about 13.6. It's just like whenever you see someone drop over the horizon on a boat at the ocean. And then you zoom in and they come back into perspective. You gain that resolution. And then it happens again. You're basically losing resolution. We lose resolution. We can't see that. We're just too small. In this aspect, we're a particle. We're like a neutrino. We're probably even smaller than a neutrino compared to the universe. But it doesn't mean that neutrino doesn't have a purpose either. 94.5 is Earth's farthest distance. 67.5 is Venus's distance. All right, so now when you change it to 13.55, it's 27.1, 54.2, 81.3, 108.4. So change it to 13.6, it's 27.2, 54.4, 81.6, 108.8, and now it's 40.8, 67 instead changed to 68, and 94 changed to 95, which is technically a little out of square, but it still works. Now let's change it to 13.7. Okay, so you change it to 13.7 billion years. Looks pretty good. 27.4 is pretty square. 41.1, 54.8. It's all right, but it starts getting a little out of square. 68.5, 82.2. Now you don't have 9 times 9 is 81, or 27 times 3. This is almost 96, which isn't fairly off from any of the numbers, but it's out square because 109.6. Now, I may add, this could be possible through latency or latency, like RAM latency or a resistor where it has a value of maybe a little more or a little less somewhere within that range. So maybe this range could be viable, but it's out of square around, it starts getting out of square about halfway through. And that's only just like one of the 6 other octones, because it's basically 8 waves here.